Good morning, everyone. My name is Fanindra, and I'm from First Year Aero, and I'm here to present my concept video presentation uh, for the topic of eigenvectors for a matrix for repeated eigenvalues. First of all, what are eigenvalues and eigenvector? If, as we all know, we have matrices, and if A is an n by n matrix and the lambda is a scalar for which Ax is equals to lambda x as a non-trivial solution which belongs to the real numbers, then lambda is an eigenvalue for A and x is a corresponding value of eigenvector A, where we can also write it as we can also write it as Ax is equals to lambda x or lambda by x. A minus lambda I into x is equals to 0. The matrix A minus lambda I is called a characteristic matrix of a where I is a unit matrix. Uh, for any matrix A minus lambda I, if we do, it will give us a characteristic equation. If we solve that a characteristic equation, then we will get eigenvalues. If we keep the eigenvalues in the place of lambda and we do separately, then we'll get the eigenvector. So let's see the process in detail. If the equation that A minus lambda I is equals to 0 is called a characteristic equation of A, and the roots of the equation are called as eigenvalues of the matrix A. The set of eigenvectors is called as eigenspace or characteristic corresponding to a lambda. The set of eigenvalues of A is called as the spectrum of A. Now coming to the characteristic equation, if A is an any square matrix of an order n, you can form a matrix A minus lambda I, where nth order unit matrix, where n is the nth order unit matrix. Okay, the determinant of a matrix is equal to 0. That is A minus lambda I is equals to A into lambda into identity matrix is equals to 0. Is called as the characteristic equation of A. On expanding the determinant, we get minus 1 whole power n to the power lambda n and k1 lambda n minus 1 and k2 lambda to the power of n minus 2 and so on kn, where k is expressible in terms of aij. Aij gives the specific position of a element, I in rows and j in columns. The roots of this equation are called as characteristic roots or latent roots or eigenvalues of matrix A, where x is a where X is a column matrix, x1, x2, and so on, is called as eigenvector and eigenlatent vector. So properties of an eigenvalues. The sum of eigenvalues of a matrix is sum of elements of the principal diagonal. The product of eigenvalues of a matrix A is equal to its determinant. If lambda is an eigenvalue of matrix A, then 1 by lambda is eigenvector or eigenvalue of A inverse 2. If lambda is an eigenvalue of an orthogonal matrix, then 1 by lambda is also gives its eigenvalue. So properties. If lambda 1, lambda 2, and so on, lambda n are the eigenvalues of A, then k1 lambda, k2 lambda, and k lambda n are the eigenvalues of the matrices K, where k is a non-zero scalar. And 1 by lambda and 1 by lambda 2 and so on 1 by lambda n are the eigenvalues of the inverse of the matrix A inverse. So, and lambda 1 whole power p and lambda 2 whole power p and so on lambda n whole power p, where eigenvalues of a power p, where p is any positive integer. And now let's know about some Cayley-Hamilton theorem. So Cayley-Hamilton theorem says that about every square matrix satisfies its own characteristic equation. So as we learned before, the characteristic equation is given by a minus lambda I, which is equal to 0. So let ij and order of n be a square matrix, then we represent the square matrix in this manner, where n by n is the number of columns and rows, and aij values of a specific elements. And the characteristic polynomial of a psi of lambda, then psi of lambda is equals to a minus lambda I, where I into lambda we take separately and we'll substitute in minus a. So a double one minus lambda and a12, because in identity matrix only in the principal diagonal or one will be there. So only then if you multiply with lambda, only those principal diagonal elements will multiply with lambda. So when subtracting from a also, we only the principal diagonal elements will minus lambda. the characteristic equation is A minus lambda I, which is equal to 0. So P naught lambda power n plus P1 lambda power n minus 1 and P2 lambda power n minus 2 and so on Pn lambda power 0 is equal to 0. When we are to prove that P naught a power n plus P1 a power n minus 1, P2 a power n minus 1 plus so on Pn I, which is equals to 0. So note 1, pre-multiplying the equation with A inverse. So we get P naught a to the power of n minus 1 plus P1 a to the power of n minus 2 and P2 a to the power of n minus 3 and so on P to the power of, sorry, P n minus 1 I plus P n of A inverse. At last we are multiplying with A inverse, right? So P n A inverse will be there. So if we remove A inverse to other side and bring back to Pn here, so minus 1 by Pn and remaining all element will write it in this form. And yes, this result gives the inverse of A. This is given inverse of A in terms of n minus 1 powers, and A is considered as a practical method for a computation of the inverse of the large matrices. Now, 2. If m is a positive integer such that m is greater than n, then any positive integral power of power a power m of a is linearly expressible as in terms of those lower degree values. So, example of Cayley-Hamilton theorem. Verify Cayley-Hamilton theorem for a matrix of a given matrix A, hence computed with A inverse. So, A minus lambda I, which is equal to 0, and that is if you remove lambda I from the A, we follow this equation, and according to our simplification, we can write it in this form: lambda q minus and 6 lambda square and so on. And we get, after solving that equation, we get some eigenvalues. So we keep it aside, and in the place of lambda, we should substitute A. So if we substitute A in this equation, we'll get as a cube minus 6a square plus 9a minus 4 is equals to 0. So now a cube will be given as a square first will be given as a into a, and then a cube is written as a square into a. So we got here a square value, and next a cube minus 6a square plus 9a minus 1. So we have a cube value minus 6a square also we have, and 9a value also we have, and I also we know it's a, so we'll get it as 0. When the own characteristic equation satisfies the matrix, then it verifies the Cayley-Hamilton theorem. Now pre-multiplying both sides by 1 by of 1 by A inverse, we have multiplied our characteristic equation with A inverse, so we get a square minus 6a plus 9i minus 4a inverse is equals to 0, and 4a inverse is equals to a square minus 6a plus 9i. If you're removing 4a on this side, and 4a will be 4a inverse will be given as we all know the remaining terms, so we should multiply them all and we'll get as 4a inverse is equals to, so a matrix, and sending 4 on other side, so 1 by 4 into the matrix is given as a inverse of the matrix. Now, similarity of a matrix. Similarity of a matrix. If A and B are two square matrices of order n, then B is said to be as similar to A if there exists a non-singular matrix such as that B is equals to P inverse of A into B. And similarity matrices is equivalent to the relation. And similarity matrices have the same determinant. Determinant can't be changed. Determinant will be only the one for any matrix. For not for any matrix. If for one matrix, if you take any 2 by 2 or n by n columns, and if you do determinant will not change. Determinant will be same. So similar matrices have the same characteristic polynomial and hence the same eigenvalues. If x an eigenvector corresponding to the eigenvalue lambda, then P inverse of x is an eigenvector of B corresponding to the eigenvalue lambda, where B is equals to P inverse of A and P. So now let's go to the topic of diagonalization. If A is said to be a diagonalizable, if it is similar to the diagonal matrix, and matrix A is diagonalizable if there exists an invertible matrix P such as P inverse of AP is equals to D, where D is the diagonal matrix, also known as spectral matrix. The matrix P is said to be diagonalized a form of A to diagonal form, and it's known as a model matrix. So reduction of matrices to the diagonalization. If a square matrix A of order n has a linearly independent eigenvectors of within a matrix B, can be found as B inverse of AB, which is an equal to D, is called as a diagonal matrix. Note and a matrix B which diagonalizes A is called as the model matrix of A is obtained by grouping the eigenvectors of A into the square matrix by substituting the eigenvectors into place of X. We'll get a model matrix. Eigenvectors will be in the form of x1, x2, and x3. And after getting them, we should write them x1, x2, x3 in a column in the columns, so that we'll get a complete matrix of the n by n matrix. Then we should for that it is taken as P, and inverse of that is taken as P inverse, and we know the default one. So P inverse into A into P is given as D, where D is a diagonal matrix. So example, prediction of matrix A to diagonal form by similarity transformation and find A cube. So as we know, we should get a characteristic equation by doing A minus lambda I, and we'll get an equation. And by solving that, we get three values. The eigenvalues are 1, 2, 3. So corresponding to 1 for first eigenvalue, which is lambda is equals 1. If you put that 1 in the place of I, sorry, A minus lambda into I. So into lambda we will get x1 as a k1, which is a constant, and 1, 0, 0. It is a first eigenvector. And coming to second one, lambda is equals to 2. If we put 2 into I, 2 lambda, A minus lambda I low, we should put lambda place 2. We will get k2 as a second constant, and 1 minus 1, 0 will be the eigenvector. And the third one, lambda is equals to 3. And if you put A minus lambda I in the place of lambda 3, we'll get another eigenvector. K3 will be the constant, and 3 minus 2 and minus 2 will be the eigenvector. So hence the model matrix M is given as, or you should write x1, x2, x3 in the form of row in a column wise. So 1, 0, 0, 1 minus 1, 0, and 3 minus 2 and 2. Det of M will be again minus 2. So inverse of matrix is given by adjoint A by det M. So adjoint of M also be found, and M inverse is given by adjoint A by det A. So delta of A was minus 2, and if you divide everything with minus 2, we get 1, 1 minus 1 by 2, 0 minus 1 by 2, 2 by 1, and 0, 0, 1 by 2. And we should to do the diagonalization, we have M inverse now, we have A, and we have M. So if we multiply them all, we'll get a diagonalized matrix, which is in the form of our eigenvalues will be in the diagonal, and remaining all of this will be 0. Now, since D is equals to M inverse A in M, M is equals to MD M inverse. So A square is equals to A into A, and A cube is given as A square to A. And if we find A cube, we'll directly get we have a diagonalized value into 3 feet into A into A into A part cube. Then we'll get a part 3 also. Hence, our value of A cube is 1 minus 7, 32, and 0, 8 minus 19, and 0, 0, 27. So orthogonally similar matrices. If A and B are two matrices of order n, and then B is said to be an orthogonally similar matrix to A, and there exists an orthogonal matrix P such that B is equals to P inverse of AB. Since P is an orthogonal, P inverse is equals to PT. Here is the orthogonal rule. P inverse, A inverse of, if A inverse is equals to A transpose, it is the matrix is said to be as orthogonal. B is equals to P inverse AP and P part D AP. Then the real matrices of order n have mutually orthogonal real eigenvectors. If any two eigenvectors corresponding to distinct eigenvalues, then real symmetric matrices are orthogonal. So example, diagonalization of a matrix is diagonalized matrix. If you diagonalize this matrix by using some lambda values, and you should find the three eigenvectors you should place in this form, and you should again find this model matrix. And here we have here in the form of root. It's also okay, but 2 minus 2, 6, 6 is a required diagonal matrix at the end. Thank you. This was my presentation of concept videos for the maths. Thank you.